Hello and welcome to lecture number 2 of my course Digital Image Processing. In this particular lecture, we will talk about image resolution, we will talk about grayscale, and we will discuss the total memory requirement of image, that how much memory is consumed when we are trying to store an image in a computer. So starting with resolution, maybe many of us are normally defining resolution as number of rows and columns. Maybe total number of pixels is defined as resolution, as we normally we define state-of-the-art cameras having 1.4 megapixel resolution, 1.9 megapixel resolution, and whatever it is. From technical perspective, resolution defines the amount of detail present in an image. The amount of discrete detail present in an image is termed as resolution, and definitely this is measured in terms of number of rows and columns. If we can reconnect our previous lecture, like lecture number 1, we have learned that the resolution or total number of rows and columns, this is actually dependent upon sampling. When we were trying to perform the process of digitization, that analog image was being converted into digital image. The very first step, it was sampling, and in the sampling stage we need to decide that how many rows and how many columns are to be acquired for representation of an image. As we normally work out in daily life, that the more number of samples we're going to take, more closer approximation we will have at the end. So accordingly, the sampling decides the total number of rows and columns. The more number of samples we are going to acquire from an analog image, the more precise approximation we will have at the output in terms of digital image. And if we are going to reduce the samples, if we are going to reduce the number of rows and columns, we will start seeing distortion in the image quality on screen. I will demonstrate this using some graphical examples in the next slide, but just to make sure that we do interpret resolution properly, that this basically refers detail present in an image. More details present, image will appear more like beautiful, sharper, more attractive, more comprehensive on screen. Less details present, it will be appearing in a bad manner. It will give us a bad appearance on screen. How? Let us see a particular example. On top right corner, we do have an original image, and this is same image I have taken from MATLAB. Original image, and initially it does have resolution of 300 by 246. Like it does have 300 columns, 246 rows, and apparently it gives us a good approximation that we are able to understand, we are able to interpret different coins present, and even we can see that some coins are larger, some coins are smaller, and even we can see that something is embossed in the coins. Now, if we are going to reduce the resolution, that is, we are going to reduce number of rows and columns, something output shown on left bottom side, this is what resolution, low resolution image, and yes, we can see a noticeable degradation in the image quality. We can see a noticeable distortion in the image quality, and we can see that there are certain fluctuations, there are certain variations, there are certain problems in these coins, and the image quality is not very convincing. Why this has occurred? Because from the original image we have reduced many rows and many columns, we have removed many rows and many columns, and as a result, within the same area, the total number of rows columns have been reduced. The total detail present within same area, it has been reduced. As a result, individual pixels, they have expanded, they have increased in size, they have expanded. As a result, we can see there is a distortion. Like we do have similar area for image representation, but this time we do have less number of rows and columns. Like we are trying to represent less information in the same area. As a result, pixels start appearing distorted. And this is what it convinces us that resolution plays a very important role in deciding that how an image will appear on a screen. If we have reduced the resolution, definitely the image quality is distorted. Okay, so let us, from this particular point, let us try increasing resolution again. If I'm going to use this low resolution image and I'm going to increase image resolution with something output shown on bottom right side, this is what we're going to get. Apparently, image quality has increased. Image quality, it has got better in comparison with the low resolution image, but still we can feel there's a difference between the high resolution image, reconstructed image, and the actual image, original one. Why this has occurred? This has occurred because we have used low resolution image, and whatever information it was available, whatever information was present, it was available in the low resolution image, it has been further interpolated in order to increase the resolution, in order to increase the rows and columns. Like whatever information was available in the low resolution image, it has been propagated, it has been interpolated in order to fill the space, and as a result we can see there is certain amount of improvement, but still this is not as good as the actual image was, because we have done this reconstruction, we have got this high resolution image from something where we already had lost some information. So just to quickly conclude about resolution, that it is amount of detail present. If we are going to reduce the detail, we will see distortion in the quality, in the image quality, and it is not very easy to come back from a low resolution image to high resolution image, because the reconstruction will be done using interpolation, that is making use of available data in the low resolution image. One more factor related to images, this is grayscale. If you remember what we have defined in last lecture, it was that images are represented in terms of computer memory. Images are stored in computer memory in terms of 2D matrices. Let us talk about a very simple 3 by 3 image or 9 by 9 image, whatever this is. So for a 3 by 3 image, we do have 3 rows, 3 columns, and there will be in total 9 individual pixels. There will be in total 9 individual elements. At any given time, value of a particular element is what we call as pixel value or intensity value. For instance, if I can show you the top image, right hand side, we can see 1 1 1 0 0 1 0 1. So at any particular given time, at any point, like at any time point, a particular pixel being referred, this is what the intensity value is. And this intensity value or gray level value, this is represented mathematically using L. This capital L, this is the notation, this is the representation in order to denote any particular intensity value 1. So this particular pixel, it is having intensity value equal to 1. The gray level value over here, this is 0, this is 1. So for a 9 pixel image, for a 3 rows 3 column pixel image, there will be 9 different gray level values present in that image. And definitely, as these are mathematical values, there will be a certain range of intensity values, and this range of intensity values is what we define as, what we name as gray level. The intensity value, the range of intensity values present in an image is what we call as gray level scaling or grayscale. For instance, in this upper image, if we can scan the individual values, the minimum value being used is 0, the maximum value being used in this image is 1. Therefore, the grayscale being used in this particular image, this is 0 to 1. And normally, this is what we define as binary image, and grayscale can be written as 0, 1, or the range is defined in terms of minimum value, maximum value. Similarly, if we can see this right bottom image, we can see different pixels having intensity values 105, 20, 250, 200, 0, whatever this is. So if we're going to establish a range, the minimum intensity value being used is 0. The maximum value, maximum gray level value, this is 255. Therefore, the grayscale being used for this particular image, grayscale being used in this particular image is to be defined as 0, 255. This means the lowest value being used in this image is 0. The highest value being used, highest gray level value being used in this image is 255. And this gray level, this grayscale, this level values, intensity level values, these are very important in deciding that how an image would appear on a screen. Again, this is quite similar. If the values being used inside an image, if this is 0 to 7, this means 8 different values are being used. 0 to 255, it means in total there are 256 different values being used for pixels. In case of binary image, 2 different values, gray level 0 to 1. As I mentioned earlier, that this gray level decides that how a particular image would appear on a screen. Please do remember the lowest gray level value, the minimum value of the grayscale, it will appear on a screen in pure dark color, in pure black color, for instance. And the highest value of the grayscale, it will be displayed, it will appear on the screen in the brightest or maybe white shade, perfect white shade. So for a binary image using grayscale 0 to 1, an image will appear on the screen in terms of pure black and white color. Another image using a grayscale of 0 to 3, 0 will appear in pure black color, 3 will appear in pure white color, and intermediate values 1 and 2, these will give different intermediate shades moving from black to white. And similarly, grayscale, when you're using grayscale of 0 to 255, 0 will be appearing as 0 will be displayed as pure black, 255 will display as pure white, and all these intermediate values, they will appear in different shades in between black and white. Maybe a pixel having intensity value something closer to 120, it might give us gray shade, and we keep on moving from gray to light gray, white, bright white, and until it reaches 255. Just to give the concept quickly, that for instance, let us say we are using a binary grayscale, and we do have a 3x3 image defined something 100101. And if we're going to display this image on the basis of this binary grayscale, this is something what bottom left, this is something what we will be seeing as an image. However, we have got one more image, and as this image coefficient values, we can see the grayscale is 0 to 7. 0 will be appearing as pure dark, pure black, 7 will appear pure white, and these remaining values, they will give us different shades in between black and white. Similarly, if we do have one more grayscale image, the minimum value being used somewhere, this is 9, the maximum value being used in this image, this is something 250. And now as per this interpretation, the grayscale, you may define this as 9 to 250, or you may define this as, in terms of binary, 0 to 255. So the lowest value, it will give you pure black shade, the highest value, it will give you pure white shade, and all the intermediate values, they will give you different gray shades moving from black to white. So it means how a particular image will appear on the screen, this actually depends upon the intensity or the gray level values. And the gray level values to be used, this actually depends upon the grayscale. And what grayscale will be there, it basically depends upon the quantization stage. If you can recall the previous lecture of digitization, that during digitization we perform 2 steps, sampling and quantization. Sampling will decide that how many rows and columns will be there, that is resolution, and quantization will decide that what grayscale is to be used, what grayscale will be used. If we are allowing only 2 gray level values, then we are saying that 2 quantization levels, it will lead to a binary image, and the more number of quantization levels we are going to allow, as a result, the more stretched grayscale will be there in 2D matrix, and as a result, more colorful appearance this image will give us on screen. For instance, the same image, the left one, this has been displayed by using a standard 0 to 256 grayscale, 0 to 255 grayscale, whereas the same coins image being displayed using a binary grayscale. We can see that a lot more detail is present. A lot of detail is present in the left image, and we can see the different coins embossed and all these things. Whereas on right hand side, we can get a very basic information of the image, that there are some circular objects present in the image. What objects are those? What is printed? What is written? We cannot get anything because we are using a very limited grayscale, and this limited grayscale, this is shop of details. We are having minimal possible details presented in binary image, or when we are using a binary grayscale. So what we can conclude from this is that the stretched grayscale, the larger grayscale, will be presenting more details in the visual appearance of the screen, whereas compressed grayscale will lead to very limited details on the screen. Discussing individually resolution and the grayscale, now let us talk about the storage requirement. Normally, how much memory is required for storing a digital image in computer? As the total storage requirement, this is basically dependent upon both factors, that is resolution and the grayscale. The more or the higher the resolution is, that is more detail present in terms of rows and columns, it will definitely require more storage. And same with the grayscale, the higher or the larger the grayscale, the stretched the grayscale means more details, more colorful representation is there. As a result, it will require more memory. In contrast, if the grayscale is compressed, that is total number of shades are compressed, definitely it will affect the memory requirements, and your image will consume less memory. In order to establish a mathematical relationship between the total memory storage or memory requirement and resolution versus grayscale, we do have a interpretation. This is like as defined in the equation, B is equal to M into N into K. So this B represents total number of bits. This again I'm repeating, this is total number of bits. Total number of bits required to store a digital image, it is M into N into K, where M into N, this defines the resolution, number of rows and columns, and K, this is very important, that this K defines total number of bits required to encode a particular grayscale. And how this K is computed? This K is computed using very famous interpretation of binary, that is 2 power n, or simple 2 power k is equal to total number of gray levels. So in order to utilize 0 to 7 gray level, that is we want to have total 8 different colors, we want to have 8 different combinations, we want to have 8 different gray levels. So we just need to write 2 power k is equal to 8, and accordingly k will be computed equal to 3. As per this equation, this is 3. And similarly, for any other grayscale, we will do computation as shown in this image. Let us talk about, for mathematical interpretation, let us talk about a very simple binary image. And we do have 3 rows, 3 columns, and grayscale being used. This is binary. So as resolution is, this is very simple, 3 into 3. Grayscale being used, this is 0 to 1. In total, how many different gray levels we want to have? 2. Therefore, let us compute 2 power k is equal to total number of combinations. 2 power k is equal to 2. And as a result, k, this is equal to 1. And now let us substitute values, 3 into 3 into 1. So in order to store a binary image using this grayscale 0 to 1, we need only 9 bits. I will demonstrate this later on in the practical as well, that we will store this image in computer memory, and it will occupy only 9 bits. In contrast, if we do have another image, let us say a 3 by 3 image, and this time we are using 8 different gray levels. 8 different gray level means different values in between 0 to 7. Let us say this 3 by 3 image, it is having value 5, 7, 3, 0, 0, 2, 4, 4, 1. So this is a 3 by 3 image. Resolution is 3 by 3, of course, and K Now this k is to be computed by using the same binary formula. 2 power k is equal to total number of gray levels we want to have. As we want to have total 8 gray levels, therefore this k becomes 3. 2 power 3, this makes equal to 8. So this k is 3. And now let us substitute this k value 3 into 3 into 3. Resolution into k. This makes 3 into 3, 9 into 3, 27 bits. So now, in order to store the same 3 by 3 image with extended grayscale, 3 by 3 image with more shades, 3 by 3 image with more colors, basically in between black and white. Now this image will occupy 27 bits. And basically what those 27 bits are, from where that 27 bits, basically from where this number comes, just to make you understand, I have done this binary interpretation as well, because but computer is a binary machine. Whatever we are going to do, this is to be converted and stored in binary. So in order to store this 5, let us do binary conversion. 5 is equal to 101. The 0, this is again 000. 4, this is 100. 7, this becomes 111. So every single value is to be converted into binary, and accordingly every single value will consume 3 bits. Therefore total there are 3 into 3, 9 elements, and every element requires 3 bits. Therefore 9 into 3, in total this image will occupy 27 bits. So this is very important to do this particular interpretation. Although this is 0, but might be, as we are using grayscale of 0 to 7, it might be there might have been 6 over here, there might have been 5 over here. Therefore every value is to be defined, is to be written in terms of 3 bits. And similarly, if we are going to use the same 3 by 3 image with extended 256 gray levels, then the memory requirement definitely it will increase, and it will go up to 3 into 3 into 8. It will occupy total 72 bits. So now we can quickly conclude that the total memory required to store digital images in computer, this is dependent upon what grayscale is being used. The smaller or the compressed the grayscale is, less memory it will occupy. The larger the grayscale, the bigger the grayscale, it will be occupying more memory, but you will be able to differentiate different shades, different colors. In binary, we will have very limited representation on a screen, but it will occupy less memory. In grayscale and color images, we will have very good representation on a screen, but it will require more memory. Maybe you can do experimentation at your own. If you are having some binary images, they will consume less space in your disk, and if you have colorful images, they will occupy definitely a lot more space. Along with this, we can go for a very quick computational table. For example, this n represents number of rows and columns, and let's assume we are talking about square images. This means 32 rows, 32 columns, 64 by 64, just for the sake of computation, 128 by 128 or 512 by 512 image, and this k represents number of bits required for encoding a particular grayscale. So a 32 by 32 binary image, k is equal to 1. It means two levels, 0, 1. 32 by 32 binary image would occupy this much memory, and 32 by 32 standard grayscale image, it will occupy this much number of bytes, 8192. And this goes on for everything. This goes on for all those images. And with respect to the resolution, definitely it is from this particular equation, it is quite evident that if we are going to increase the value of m and n, more rows and more columns are being inserted, definitely total number of bits required will increase. If we are going to decrease the values of m and n, less number of rows and columns will be there. It will definitely require less memory. So total number of bits required to store a digital image, this depends upon resolution and grayscale being used. In short, this all depends upon the detail we are going to pack. More detail we are going to pack, more beautiful image will appear on the screen, more memory it will occupy. Less details we are going to pack, distorted it will appear on the screen, and it will occupy less as well. And in normal practice, we do have to establish a sort of balance or compromise in between image quality and memory requirements. So that's all for today. I will soon upload the practical implementation for this particular lecture, and we'll keep talking about imaging and image processing in our next lecture. Thank you so much.